Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants. And today we are looking at work and heat formulas. The first example that we're going to work on says a gas expands from 1.0 liters to 5.0 liters at a constant temperature. That is an essential key of information, constant temperature. Calculate the work done by the gas if it expands in a vacuum, and alternatively if it expands against a constant pressure of 2.1 atmospheres. So the first thing we're going to want to do is separate this out into two separate formulas. One in which the gas expands in a vacuum, and the other is working against a pressure of 2.1 atmospheres. So the formula for work is at a constant temperature, so we don't have to worry about temperature. So work formula is work is equal to negative pressure times the change in volume. And that's the formula that we're going to be working with today. In our first example, because it's in a vacuum, there is no pressure. So in example 1, which I'll use in black, pressure is equal to 0. Well, any number times 0 is going to be 0. So therefore, we can just plug this in. We don't even have to calculate the volume. 0 delta V is equal to work. Therefore, work is equal to 0. So anytime you're trying to see if work is done in a vacuum, it's always going to be 0 because it's not working against anything, unless, of course, that work, the pressure that it's exerted upon the item is not due to the atmosphere or the surrounding gas. If it's a pressure exerted by a piston, let's say, even in a vacuum, depending on the situation, could exert a pressure. But in this particular case, it's simply talking about the pressure exerted by the atmosphere, the fluids around this gas that's keeping it from expanding into infinity. And in a vacuum, gas expands into infinity, or as far as momentum will take it. So in this particular case, think about it in terms of if you had a balloon and let it go in a room, it would expand into the room only so far as to where the edges of the room are. Whereas if you were to just go into a space shuttle and put it outside the space shuttle and let the balloon deflate outside the space shuttle, the gas could go anywhere, and it would go easily anywhere because it had no constraints on how far it could go. So that's kind of a conceptual process, but it's not entirely accurate, but it's good for conceptualization. So our next part of the problem asks if it expands at a constant pressure of 2.1 atmospheres. So we're going to come over here and rewrite this as work is equal to negative pressure times the change volume. And when we do that, we're just simply going to account for the pressure, which is negative 2.1, because we have a negative in front of pressure. And then we're going to multiply that by the change in volume. Change in volume is given in the first sentence as expands from 1 liter to 5 liters. And whenever you're doing the change in volume, you're going to want to start with your final volume and subtract your initial volume. So it's going to be 5.0 liters minus 1.0 liters, which in turn, when you do the arithmetic out, will get you to have negative 8.4 liter atmospheres. So we could leave it at this, or we could convert it to joules. And let's go ahead and do that process. So if you're going to convert liter atmospheres to joules, you simply multiply it by its conversion rate, which is there are 101.3 joules per every liter atmosphere. Which, again, doing the arithmetic out, is negative 8.5 times 10 to the 2, 10 to the second power, joules. And that is the work done for this particular problem. Let's do another problem. The work done in compressing a certain gas in a cylinder is 624 joules. During the compression, there's a heat transfer of 281 joules from the gas to its surroundings. Calculate the energy change. So now we're looking at heat transfer. And whenever we're looking at in terms of that, we're going to want to identify the formula that's most appropriate for this. And we're looking for the energy change. And energy change is going to be our delta U. So with delta U, of course, if you check your book, you'll know that its formula is Q plus W. W is equal to work, and Q is equal to the heat transfer. It's heat. So we need to identify which one's work, which one's the heat that's being transferred. 624 is the work done, 624 joules. And the heat transferred is 281 joules. So we simply have to plug that in. The thing to recall is that when heat is transferred from the gas to its surroundings, it is exothermic. That means it's putting off the heat. It would be hot to the touch, versus endothermic, which would be cold to the touch and is drawing energy to it. So delta U is equal to 281 joules, but we're going to make it a negative 281 joules because it's exothermic, plus the work done. And it's the work done in compressing a gas in a cylinder. So we can leave that one positive. So 624 joules. Doing the arithmetic out, you will find that the answer is simply 343 joules.